Okay, brief summary. For any matrix, the matrix equation AX equals lambda X, if there's a solution, gives us vectors X that stretch space along their line, okay, by factor lambda. And you can look at the description I did, the hand-waving description at the beginning of the original video where I kind of gesture that out. Okay, well, this equation is solved by the following steps. X is the same as IX, where I is the identity matrix, so the equation becomes this. Subtract this from both sides, well, the equation becomes this. Now, lambda times IX is I lambda times X by properties that I hope we've proven and we understand. And then we can factor X out and we get this, okay? Now, what we're trying to do is find non-zero vectors X that give us non-zero multiples of themselves. Actually, you know, I said a zero multiple isn't valid, but it actually could be. They kind of have a whole line that shrinks down to zero. Okay, well, anyhow. If this matrix A minus lambda I is invertible, then X is equal to the inverse of that matrix times the zero vector, which is the zero vector. Okay, so we're not interested in cases where this matrix is invertible. Okay, that's uninteresting. If, on the other hand, A minus lambda is not invertible, then the determinant of A minus lambda I, of course, has to be zero, because if the determinant's anything but zero, the matrix is invertible. Okay, for given matrix A then, A minus lambda I is equal to, well, here's our given matrix, this, and lambda times the identity is just this, and we can easily see that. Subtract this from this, we get this. Subtract this from this, we get this. Okay? So the determinant of A minus lambda I is the determinant of this matrix. And the determinant of this matrix is easily seen to be this, which is lambda squared minus 5 lambda plus 4. Now we're looking for values of lambda that make the determinant 0. Well, okay, if the determinant of A minus lambda I is 0, well, that means that this lambda squared minus 5 lambda plus 4 is 0. And this is a quadratic equation in lambda, so we can solve it. Now, this one happens to be easily factorable, and we solve it, and I don't go through the details. You can solve quadratic equations. It factors into lambda minus 1 times lambda minus 4 equals 0, so lambda equals 1 and lambda equals 4 are solutions. Okay? Now, for the solution lambda equals 1, we take the matrix equation A minus lambda IX equals 0. Well, remember, we're trying to solve this for X. Okay? So that equation becomes what? Well, if lambda equals 1, A minus lambda I, well, that's what this is. Remember, A minus lambda I is this. And if lambda is 1, 2 minus 1 is 1, 3 minus 1 is 2. So we have 1 and 2 here, and our 2 and 1 here aren't going to change, so we get this equation. And this equation translates to two simultaneous equations that we can easily write out. And in this case, the two equations are identical. Okay, and in this case, in general, they will either be identical or they'll be multiples of each other. So, x1 is equal to negative x2. If you choose x2 as your free variable and call it t, you have negative 2tt, and that's equal to t times negative 2, 1. Meaning that any multiple, negative 2, 1, or any multiple of negative 2, 1, any non-zero multiple of negative 2, 1, is going to have the property that when you plug that vector in here, x equals negative 2, 1, or any multiple thereof, you're going to get lambda times that vector, lambda being 1. So any multiple of negative 2, 1 is going to give you just that multiple of negative 2. Well, same vector, you're going to get out of it the same vector you put into it since lambda equals 1. Now, for lambda equals 4, we get, again, plugging 4 in for these numbers, we get this matrix times x equals 0, and you can solve that very easily. And you find that x1 equals x2. So that x is s times 1, 1, any multiple of 1, 1. Okay, so we would say then that 1, 1 is an eigenvector with eigenvalue 4, meaning 1, 1, or any multiple thereof, plugged in to this equation is going to give you 4 times that vector. Meaning that in the direction of the 1, 1 vector, the plane is going to be stretched by a factor of 4. In the direction of the negative 2, 1 vector, okay, x is here and y is here, negative 2, 1 is over here, your plane is going to be stretched. It's not going to be stretched, it's going to stay with a factor of 1. And we can picture that, and maybe I'll go on and do another video where I do that.